Okay, thank you for the opportunity to give this review talk on the activities of CREDO ML group. I will not focus too much on technical details of all these papers I will discuss, because in fact all of them deserve their own talk. So I will just more generally talk about the activities undertaken by CREDO ML. Okay, so let me start from presenting, I would say, the most stable composition of the CREDO ML task group. As you can see, most people are currently based at, I don't know how to properly pronounce it, because in English this abbreviation is mostly meaningless, but this means historically Academy of Mining and Metallurgy. So currently it's AGH University of Krakow, but there are also colleagues from Krakow University of Technology, Pedagogical University of Krakow, which also changed the name recently, so this is the current version, and also people from Institute of Nuclear Physics, Polish Academy of Sciences. So what are the CREDO ML most interests? So we are originally we were mostly focused on developing the software for CREDO detector application. But with time, this task was in fact redirected to special CREDO group called CREDO App. So I will not focus too much on these kinds of activities. So what really took our time was originally the recognition, also background subtraction, noise reduction, things like that, performed with artificial intelligence methods, of course, all in respect to cosmic ray signals. More recently, we also dealt with discovery of anomalies and novelties in cosmic rays signals. This, of course, is very interesting topic related to new phenomena in physics. And really very recently, we also got interested in analyzing collective cosmic ray phenomena, so analyzing not only individual particle tracks, but trying to model entire distributions. And in particular, we are interested in simulating extensive air showers and cosmic rays ensemble, of course, in this order, because the first one seems to be more elementary. This is, of course, a pretty complex phenomenon, which requires both extensive simulation first, and then application of advanced machine learning methods, which I will discuss a bit later. Okay, so let me first introduce CREDO ML timeline, because I think this is pretty remarkable. Its history is pretty recent, so we can in pretty detailed way reconstruct all stages of our activity. So CREDO ML era, in fact, started. We even know detailed date, because this was the talk by Piotr Homola, April 18th, 2018, at the department seminar at Pedagogical University in Krakow. Piotr gave the talk about, here's the title, Cosmic Ray Extremely Distributed Observatory, New Opportunities in Astroparticle Physics and Beyond. So this was a kind of inspirational seminar gave by Piotr at our department. And after that, the avalanche of events happened. So soon after that, I thought that it would be interesting to offer the diploma thesis related to these matters. And Darek Burakowski, my MSc student, took effort to write from scratch the prototype of new algorithm of particle detection with Android devices. And this thesis was defended in 2019. And soon after that, formally, our previous university, namely Pedagogical University, formally joined CREDO. And CREDO ML era, again, started soon after that. unfortunately, we were not able to reconstruct the detailed data, the exact data, but most likely the idea emerged sometime in winter or early spring 2020. Unfortunately, our Slack was canceled because we had all our discussion on Slack, but we have a free version of Slack, so this history is unfortunately lost. But this has to be sometime winter or early spring 2020, where CREDO ML idea was born. And again, there are some considerations, some initial work, and the first tangible result of these studies was the Marcin Piekarczyk talk at, again, UP seminar concerning the classification of cosmic ray tracks with machine learning. And then there was a plethora of various talks, seminars, and other activities related to discussing the modeling of cosmic ray signals with machine learning methods. There was Tomek High seminar in February. There was our guest from Canada, Thomas Anderson, seminar a month after that. In fact, a few days after that. Then was the talk also in March by David. And as you can see, there was pretty dense activity because almost each month there was a talk at the seminar regarding machine learning activities for CREDO. This culminated in the seminar we organized in autumn 2021 at Pedagogical University, where also a few talks related to machine learning studies of cosmic rays were given. Also the talk of Tadeusz Wibik from Łódź. Also important milestone in this history was the integration of Thomas Anderson code, which was working on, and it's still working on, iPhone devices within the CREDO data acquisition system. And this happened in March 2022. And this was mainly the effort of Michał Frączak, Sławek Stugling, and Michał Niedźwiecki. And then again, the same year, a few weeks after, there was a talk by Jurek Pryga, which was, I think, related to initial stage of his PhD studies, or final stage of his Master of Science diploma studies. Another milestone was the presentation of this all results. There were also some nuance by Tomek and Marcin at EKAI conference in Krakow. And in the meantime, we transferred, Marcin Piekarczyk, Tomek, and me to AGH, and we immediately realized that it would be a good idea to formally bring AGH to this collaboration. So this resulted in formal signing the Memorandum of Understanding by AGH in October last year. So as you can see, pretty recent milestone was the new version of CREDO detector application for Android, which was just 2 or 3 months ago. So as you see, the activity is pretty dense. A lot of things happen. This also is reflected also in the publication effort. So I will not discuss it detailed, but you can see that between 2020 and 2023, in fact, we published 4 refereed papers by CREDO ML, and they were affiliated officially with CREDO. There are also a few papers not officially affiliated with CREDO because they were performed with some external collaborators, but they are still concerning the things related to CREDO activities. And also there was some conference participation. So let me move on to more detailed discussion of what we are doing. So first we are taking care of mobile application CREDO detector, but as I said, formally this is now under the umbrella of CREDO app task group. Here's the brief statistics of how much data these applications collected so far. So there are, roughly speaking, 50 million events collected with both Android detections and iOS devices. Of course, this iOS data collection is pretty recent, so there is much smaller amount of data collected. We are also conducting active research into different directions. For example, this is mostly activity of Tomek and Marcin Piekarczyk. Because general problem with applications based on mobile devices is that they are pretty strongly reliant on the limitations of the software. So we got interested in a bit simpler device, which we have much under control, like, for example, Raspberry Pi devices. And it turns out that they also very nicely register familiar tracks of cosmic rays. So this was briefly about detectors. Now let me move on to our data analysis. So first, our data analysis focused on triggering cosmic ray events, because the common fact related to registering events with smartphones is that there is a lot of various noise sources, artifacts, and similar undesired signals, which somehow have to be filtered out. And I think this was the topic of our first paper, where we invented the convolutional neural network architecture that was used to filter artifacts and noise. And it performed pretty nicely. Here are the examples of true signals. Here are the examples of signals which were filtered out by this neural network. Pretty recent, this is publication from last year. Pretty recent is the paper which I wrote with people from Department of Electronics at AGH, where we use completely different architecture of so-called Siemens spiking neural networks, which were again used to filter out artifacts. But architecture was different, but the performance was pretty similar. As you can see, here are the typical signals. Here are the typical artifacts obtained with this method. Then we moved on to a bit more detailed analysis, where we singled out not only signals versus artifacts, but we tried to understand and to differentiate various shapes of signals. The standard terminology is that we isolate dots, tracks, worms, and artifacts. And more on that, artifacts can be pretty easily differentiated from dots just by looking at two parameters of the signal, namely the number of illuminated pixels in the CMOS array and the total luminosity. So those are typical artifacts. Those are dots. So this is simple. What is complex is differentiating tracks from words, which is pretty intuitive. So we developed pretty advanced set of statistical classifiers, which were able to differentiate the signals. Of course, there were many trials and errors to obtain these results. We tested various models, various architectures, but all in all, the net result is that we were able to obtain accuracy above 90% in all cases. We again tested several architectures for that purpose. This is another example with convolutional neural networks. Of course, they had various performances. We also developed our own architectures. So as you can see, for all types of signals, the accuracy close to 90%. Then we moved on to the problem of searching for anomalous phenomena. This is a pretty complex problem, because looking for anomalous phenomena is already statistically complex, because various anomaly detection algorithms isolate various signals as artifacts. So this is pretty unsatisfactory from the practical point of view, because if we use various algorithms, we have various things as novelties, as phenomena, which is quite nice. So our idea was to use several models at the same time and look for the joint set so that this procedure becomes quasi-deterministic. So this is the scheme of our architecture. This is so-called autoencoder, which is basically consisted of two neural networks and the so-called latent space in the middle. And we look for anomalies by analyzing this latent space. And here's the master plot of this analysis. This blue and yellow curves show the typical models, which at the horizontal line show the percentage of things which are treated as anomalies, and at the vertical axis show the percentage of things which are treated as anomalies by two models. And we invented a set of models consisting of so-called agglomerative clustering and the DB-scan. And you see that for pretty small statistics of anomalies, they are superior by considerable factor than the other solutions. So here's again the thing which is treated as a typical hit, and here's the thing treated as anomaly. There are also other architectures which we develop. This is the architecture based on so-called eigenfaces approach, which we dubbed eigenhits. You see that things treated as anomalies are again pretty non-standard. Another approach based on so-called rough sets, also developed very recently. It shows standard tracks and anomalous tracks, and here are comparisons of two versions of this analysis with standard k-means method and so-called rough k-means method, which evidently show anomalous signals, but looks like this approach based on rough sets is a bit better because it's not contaminated by standard signals. A future perspective. So generally speaking, there are such 4 branches of machine learning based on discriminative and generative and supervised and unsupervised training. So far we dealt mostly with discriminative, supervised and unsupervised methods, and now we want to head towards using more actively generative methods. And here's the example of the training data set used for that. So these are pictorial views of cosmic ray distributions, which we prepared for the purpose of this paper. And finally, I got into my summary. So looks like the efficient methods of classifying the individual signals are already in place. What we are now endeavoring is more versatile use of generative methods aimed at analysis of distributions of signal, unfolding detector effects, and general collective phenomena in cosmic rays. Thank you.
Thank you very much. Questions? Simon?
I wanted to ask about this paper where you classify dots, tracks, swarms, and artifacts. And there you had this, if I remember correctly, you had a test and training data set of 2,500 hand-labeled pictures or something like that.
Yeah.
But what and worms and artifacts turned out to be classified worst, kind of. So
No.
But my question would be, what I could not find is distribution in this test set of how many dots, tracks, worms, and artifacts you had in the training, basically.
Well,
because I would assume that since the structure of worms and artifacts is more complex, you need more of these in the training to get the same results.
Basically. Yeah, that is a good question. So we manually labeled a set of, as far as I remember, over 1,000 of events. And this set was manually balanced. It does not reflect the distribution of hits in the original data set. So it was done just for the purpose of better training. Yeah. Also, those are kind of trivial. So they have pretty simple morphology, so you don't need so many.
Okay, thank you very much. I don't see any remote hands raised, so just my quick summary of your talk. Please correct me if I'm wrong. So the machine learning is a must tool for the analysis which is currently running or planned within a concept like CREDO. And I'm very happy that we have a very professional task force, and it's already efficient in producing results in form of articles. And we, of course, count for more. And it's not only technical, I need to emphasize. It might be that we will receive critically important hints from this area, from machine learning, from AI, to really understand the key physics behind our observations. Is it less correct?
I guess so.
Okay, let's thank Łukasz again. One question, one last short questions. Marek, would you like to say something? Marek Więckowski?
Tak, ale ponieważ mój angielski nie jest zbyt dobry, dlatego napisałem przez translator. Proszę przetłumaczyć.
Tylko musisz to powiedzieć.
Jakkolwiek robione testy związane na przykład z bombardowaniem imionami matryc CMOS telefonów komórkowych, tak aby zweryfikować poprawność modeli rozpoznawania. Czy faktycznie imiony zostawiają takie ślady na matrycy, jak my rejestrujemy je w naszych detektorach?
Maybe I will start with translating. So Marek is asking whether there were any tests by shooting at matrices with particles like muons. So this is hard to have a muon source. So I'm not aware of any tests like that. I'm beginning to answer. Sorry, Łukasz. But then you will have a second to add something. So this is hard. We have another proof that smartphones or pixel cameras see muons, and this is an article by Tadeusz Wybik, who is connected today, I believe. That the distribution of the lengths of the tracks, straight tracks left on matrices, is compatible with the expected distribution of zenith angles of muons. So this is very strong. This is published. If it comes to other particles, there were tests, of course, with radioactive sources, but not in our collaboration. There are other groups, other collaborations and articles. Of course, we would be happy to have own resources on that. So this is one of the topics we should proceed with if we want to understand better the tracks. Now, Łukasz, your turn.
Okay, I of course fully share Piotr's viewpoint. Just to add something to this, notice that in our analysis, we generally refrain from interpreting the signals in terms of particular particles. So we of course, this interpretation is interesting and should follow, but we generally operate in terms of dot, tracks, worms, and artifacts. Of course, we tend to think of tracks in terms of muons, but since this is, we are just focused on morphology at this, at least at this stage. I don't know if this saturates your question.
Okej, Marku, jesteś zadowolony z tego? Co?
Tak,
jest. Trzeba przetłumaczyć, czy myślę, że jest wszystko jasne, tak? Super. Let's thank the speaker again.